Alright, I'm going to just go a little bit of this video. I feel like Professor Dave does a really good job and he has nice animation, so I'm not going to beat a dead horse here. But the first thing I wanted to show you, I worked through this again. So when we do our work here, we can't forget the cosine theta because the, the displacement, um, as you're moving that book, you're holding the book up, but then you're walking straight across. Um, so you're not like pushing on the book, you're just walking it at a constant rate. So the angle here is a 90-degree difference between the displacement of holding up the book in a stationary fashion and walking forward. Okay, um, so you work through this equation: force, distance, cosine theta. And right here I showed you how Professor Dave went through that really quick, but you can replace force with mass times acceleration. That's how I got that 500 the last time I did this. 50 kilograms, 9.8 meters per second, 1,000 meters, and then cosine 90 degrees. Because you're still not technically like lifting the book up or down. Um, you're not like doing work on the book. You're just moving forward. So that's demonstrated by this, the fact that um, when you have cosine 90, this ends up coming out to 0. So when you multiply everything by 0, it's 0 joules. Okay. So, because technically you're not doing any work on the book because that's your stationary and you're moving at a constant rate in the forward direction. Even though, and that point is made, even though you're tired, it's still going to be no work on the actual book itself. It's work on your whole body. Okay. I went over this one. This one's correct. Um, so I've kind of talked through this one too. You need to think about this in your next set of equations. If applied force does positive work, it moves in the positive direction the way the force is. Excuse me. Okay. If it's negative work, that means you're like trying to stop a car going down the hill, right? You are trying to prevent it from rolling down the hill, but it's still rolling. So your negative energy would be like frictional force. Okay. And then there's two forms, potential and kinetic. Potential is the really easy form. It is the energy that it takes to keep, like that it could potentially have. So Professor Dave explains that, well, the higher you raise something, the greater energy it could have in its fall. So you increase potential energy just by moving it higher away from the earth. Um, but it's how much potential does it have? How much stored energy? And kinetic is moving energy. Okay? So some more work equations. I worked through this before. Okay, kinetic energy. So potential is literally just like how much is stored. I don't know why it doesn't really go over potential here. So Professor Dave hit it hard, and it hit it hard in the physics classroom. So if I kind of go back to potential energy real quick in the physics classroom, just ensure that you understand this equation. Gravitational potential energy, which is the common one, is mass times gravity times height. So notice the higher the kid is in the swing, the higher the potential energy. And it's lowest when he's at the bottom point, right? So each time you move this ball up the stairs, and hopefully you work through this quick quiz, you increase its potential energy. Because if I push it off of this stair, it's going to have a greater change in energy than if I push it off of this stair, stair D. Okay, so same thing with springs. When you're using like those Nerf guns, those compressed springs demonstrate elastic potential energy. So stretch or compression is X. So it wouldn't hurt to kind of jot this down. To do the spring energy, it's 1/2 the spring constant, whatever it is that they give you, which is usually a given number, times the compression squared. Okay, so hopefully you work through these. There's not many of them. But that's it for potential. And then when you got onto kinetic energy, which you read through, gave you the equation, it talks you through. I'll kind of go through this real quick. Kinetic energy is motion energy. Anytime somebody is moving, they have kinetic energy. The faster they move, the greater the kinetic energy. Okay? So unit is joules. So here, 10 grams, please convert to kilograms. This should be in kilograms. So you need to do that conversion. 10 grams. I think, check my work here, 1,000 grams. So no, it's like really big. Hang on. Let me think this out real quick. Grams is base. Oh no, I was right. 1,000 grams to 1 kilogram. Okay, do your conversion, and then this needs to be converted the other way. 1.2 km, and there's 1 km to 1,000 meters. Run that mass and multiply that by 1,000. Okay, now you can put it in the K. E is equal to 1/2 mb squared. So once you get your answers, plug this one in here, plug this one in here, and solve. Okay. Now, if the speed is 1/2, we're decreasing by a factor of 4 because you have to consider that square. And when it is doubled, you are increasing by a factor of 4. So you can just kind of look at the answer you got and divide it by 4 or multiply it by 4. And this comes up in the physics classroom as well. All right, I'm going to introduce this a little bit, but this slideshow, I'm not sure I'm a big fan of how it introduces it. This one, let's scroll to the top. So I'm ready. This jumps into the next section because mechanical energy. So this is important to know. Mechanical energy is just Ke and Pe together, right? So if Pe increases, Ke decreases. So at this point, power is work divided by time. How much work are you putting over a given amount of time? Okay. So, and we'll come back to power here in just a sec. But when we're going to go ahead and I'm going to back this up. I'm going to have you just kind of look at, I'm not sure, these labs aren't always super amazing, but I'm at least going to have you look at the PhET simulation about power, which I'm not sure it's in this. Do we have it? Pardon me while I look. There was a link for a while, and I don't know if it's in this one. So if you take a look at the PhET simulation, which I will post, researched it. The energy skate park. I'm just going to play around with this one. So if I open, just play it. You shouldn't have to download it. You should just be able to open the activity. So I'm going to have to kind of mess with that. But what you should see when you do this, clearly I'm struggling, is that as your, so you can kind of see in this video here, they're going to have different references or different Bar graphs and mechanical energy should always remain the same, but then potential and kinetic energy are the ones that are actually going to change. So download or then work. Aha. Okay, maybe you do have to download. So if you take a look at this, I'm going to put in the bar graph. I'm going to move my face over here. Bar graph, or you could do a pie chart. However you want to do it. Put the girl up here. The higher you go, the higher the potential energy is. Then you let it go. Kinetic gets the largest at the bottom and the smallest at the top. I wanted to do this one and put her here. Same thing. If I do large mass, you can see the pie chart kind of moving with it. So this gives you a good idea. And then there's this playground that you can put in the, if I make this really high and I put the girl up here, do a pie chart, and she died. Okay, so, whoops. So this also plays into Newton's, the Newton's law idea. So you need to make sure the other side of this is at least as long. So I need her to come back. And here she goes. That's a potential. The higher she travels, notice friction is going to slow her down. So if I put no friction, it's going to change. So if I put her up, okay, there you go. That's the basic idea. I'm not sure I'll do a lab with this just because I think you get the concept, I hope. All right, that's all for now. Hopefully that helped. And we'll pick up work energy theorem soon.